Hello, Neutrinos from home. This is Francis Racine. I'm an assistant professor of physical astronomy at the University of New Mexico, and I was tasked by the organizers to give you a pedagogical talk on neutrinos and cosmic tension. So this is a talk that's very much aimed at non-expert in neutrino cosmology, and it will cover, of course, the importance of neutrinos in cosmology and describe the effect that neutrinos can have on cosmological observable. And the meat of this talk, of course, will be about cosmological tension and how neutrinos could play a role in in these tensions, and I'll end the talk about talking about the current status of neutrino interaction as well as future prospect from cosmology. Now, neutrinos are an excellent probe of physics beyond the standard model, and that is because they appear in the standard model through this gauge singlet LH operator, which is one of only three renormalizable portals in which new physics could be coupling the standard model. So it is therefore a very well-motivated endeavors to search for new physics within the neutrino sector. And as part of this talk, I will really be focusing on the cosmological impact of potential new physics on the neutrino sectors. Now, neutrinos are very important for the cosmological evolution of the universe, and that is because at very early time, they formed 41% of the energy density of the universe during the radiation-dominated epoch. And the other thing that makes neutrinos very unique is that prior to the epoch of hydrogen recombination, neutrinos were the only free-streaming species in the universe. And that plays a very, very important role because the fact that they're free-streaming species mean they affect gravitational potential in the early universe in very specific ways. Now, a note on nomenclature here. Through this talk, we'll assume the neutrino energy density is parameterized via this parameter n effective, which is essentially an effective number of neutrino species. And in the standard model, this number is not exactly 3 because they obtain some energy through the E plus E minus annihilation, and this number is about 3.044. And so this number n effective will come in the talk at various places. Now, neutrinos, because they are free streaming in the early times, play a very important role, and that is because they can propagate faster than the photon baryon sound waves that are propagating in the early universe. And that is because neutrino is streaming, that is, they're just moving along geodesic in this straight line. And as is in this movie here, there's this green line here that gets ahead of this photon baryon plasma, which is in red and blue here. And because they can get ahead, it can gravitationally tug on the photon baryon sound wave, which would affect the amplitude and phase. So just kind of focusing here on a single time frame of such a movie. So here I'm illustrating essentially a neutrino and photon density fluctuation on the y-axis as a function of spatial distance here. And we see in this dash dotted line in black here, this neutrino fluctuation are free streaming out of some initial energy density fluctuation. And because they're streaming, they can get ahead of this big photon baryon sound wave, which is kind of coherently propagating through the universe. Now, because it can get ahead, this part that is ahead can gravitationally tug on the photon baryon wavefront here and change the phase and the amplitude of the sound wave. And you can see here, this tug results in a slight difference in amplitude. So you move from this kind of blue, red line here to the green line, and that is different both in phase and in amplitude as compared to a universe in which there would be no neutrino free streaming species. Now, mathematically, the amount of amplitude suppression that you get in going from, say, the red to the green, as well as the shift in phase of these photon baryon sound waves, is directly proportional to this R nu, which is essentially the relative abundance of neutrinos compared to the total radiation budget of the universe, which is roughly, again, this 40% number that I mentioned just before. Now, the way we can observe these little shifts in phase and amplitudes is through observations of the cosmic microwave background. So here is a picture of the universe as it stood about 380,000 years after the Big Bang. This is a map of photon temperature where we have removed the mean temperature. So you're seeing slight deviation from the mean, with the blue being slightly colder than the mean and the red slightly hotter than the mean. So the universe at the time is very, very uniform up to these small fluctuations, which are roughly at the level of 1 part in 10 to the 5. Now, the way we analyze a map like this is by essentially doing Fourier transform in harmonic space to compute power spectra. And here are the key power spectra that we compute in cosmology from such maps. This includes, of course, the temperature power spectrum, as well as the polarization power spectrum, because the CMB is actually polarized from Thomson scattering near the surface of last scattering. And you can also have the cross power spectrum from these two here. Now, the way that neutrinos free streaming affect these power spectra is again via this gravitational tug, which shifts the phase and the amplitude. And we can see this phase shift and amplitude shift directly from these spectra themselves. And this is illustrated here from a paper by Wu et al. And here, the different color lines illustrate different values of this parameter N effective that I mentioned earlier, which tells you about the abundance, the energy abundance of neutrinos in the early universe. As you can see, as you change N effective, you change the amplitude of here, the temperature power spectrum. And in going from the top to the bottom panel here, what the authors are doing is they're trying to fix and adjust the amplitude to really isolate this phase shift that I mentioned that is responsible, that is coming from this gravitational tug that neutrinos exert on photon baryon sound wave. And you can see that once you compensate for all the amplitude shifts and all that, the main effect of these spectra from having streaming neutrinos is the fact that these acoustic peak here are slightly shifted in phase. Now, the question, given that we have this effect, the question that we want to ask is this simple picture of neutrino free streaming in the early time, is it compatible with observation that we have of the cosmic microwave background? Now, this is a field that has a long story. As soon as some of the first cosmic microwave background observation were taken in the 90s and the early 2000s, people asked this question about, is this free streaming picture of neutrinos in a very early universe, is it compatible with observation? And indeed, people found that it was. So here's some of the first tests that people did back in the days was to think about the neutrino as a fluid parameterized by two effective parameters. Here, C effective, which is essentially an effective sound speed of the neutrino fluid, as well as the viscosity parameter, C viscosity, describing the viscosity of this neutrino fluid. And if the standard picture of the streaming neutrinos was accurate, then these two parameters should admit a value of 1/3. And the early analyses that people did found pretty good agreement with the standard picture of streaming neutrinos prior to the epochal recombination with a C viscosity value compatible with 1/3. Now, this parameterization using this fluid here, as some limit, it's a good parameterization to ask the question, do we have consistency with neutrino free streaming in the early time? However, it's not a very good parameterization to ask the question whether there's new physics going on at early time, because it's actually really difficult to map new physics directly to these two effective fluid parameters. So hopefully I convinced you so far that neutrinos are a good probe of new physics, and that cosmology, because it can probe things like this phase shift that I just mentioned, can probe whether the neutrinos is coupling to new physics or not. And right now in cosmology, there's something really interesting and maybe slightly worrying is happening, is that we have certain tensions between different kinds of observations going on in cosmology. And the question I kind of want to ask in this talk is whether the fact that cosmological data is sensitive to neutrino physics, could it be that neutrino physics plays a role in some of these cosmological tensions? So since this is a more neutrino-focused talk than a cosmology talk, I will briefly review these tension that I've been talking about. And of course, the elephant in the room is the Hubble tension. And this is essentially an ongoing discrepancy between CMB-based measurement of the Hubble constant, describing the expansion rate of the universe today, and in compared to CMB-based measurement to distance ladder-based measurement that are built by building carefully calibrated distance ladder to nearby galaxies and eventually supernovae. And if you compare the value of this Hubble constant that you get from these different approaches, you tend to get different answers. And some of this discrepancy can be very large, especially when you compare Cepheid to the cosmic microwave background inference of H0 with some other technique. This other distance ladders based, say, on the tip of the red giant branch, having values as somewhat intermediate. So the jury is still out there exactly what's going on here. But it's pretty clear that at least Cepheid-based measurement and CMBs are rather incompatible in terms of their Hubble constant. Now, the other important tension that is going on right now, although it is not as statistically significant as the Hubble tension, is what we call the S8 tension. And this is essentially a discrepancy between different inference of the amplitude of matter fluctuations that we have in the universe today. Now, again, it comes from comparing kind of CMB inferred values to more local measurement of structure. So if you measure the CMB, it's light coming from the very early universe, and we can take these measurements essentially extrapolate them to today to compute what should be the amplitude of, say, matter or dark matter fluctuations today. And then we can take, probes of this large scale structure like galaxy clusterings or maybe gravitational weak lensing to directly measure this amplitude of structure. And the two measurements don't really match as illustrated in this plot here. Of course, it's not, you can see that the tension by comparing the gray to some of these bigger ellipses here. And again, it's not statistically significant. It's not super statistically significant, at least not at the level of the Hubble tension, but it's still something to worry about because if we have a consistent cosmology, these two things should agree. Now, for the remainder of this talk, I'm going to be talking about neutrinos and new physics and how this new physics could impact cosmological tension. Now, neutrinos affect cosmology in primarily the three ways, via their free streaming, via their energy densities, and by the fact that they have masses, they have non-vanishing masses, which we know from oscillation experiment. And for this talk, I'm probably going to focus on the two first impact. That is, we're going to be talking about changing the energy density of neutrinos because maybe they have a non-standard thermal history. And we're also going to introduce new physics that will affect their streaming history. So we're going to affect these phase shifts and amplitude shift that I mentioned earlier. And of course, this is a field that has a long history. There's been many, many works, some of them listed here, that have tried to explore the potential of new physics and their impact on cosmological data. Now here, since we want to focus on changing the streaming of neutrinos, we're going to introduce new physics that suppress free streaming. And the way we're going to do this is just by simply postulating that there's some interaction that allows neutrinos to interact of themselves. They don't interact with dark matter or other things. It's purely a self interaction within neutrinos that will suppress the streaming here. And you can imagine that there's some new mediator coupling neutrinos with each other, and then we're going to go in the low energy limit, where this is essentially a 4-neutrino interaction characterized by a dimensionful coupling constant here. And typically, if you want to affect cosmological evolution and to have a non-vanishing impact, this coupling constant should be larger than the electroweak Fermi constant. Now, I refer you to this Berry-Manninel paper if you want to have explicit model that could be used to build such an interaction. As far as this talk is concerned, I'm just going to assume that there is such interaction as suppressed neutrino free streaming, and we want to study the impact that it can have on cosmological observable. Now, the impact that it has at first order is that it suppresses free streaming. Neutrinos are no longer going to be free streaming in the early universe as they are in the standard model once the temperature fall below 1.5 MeV or so. So in other words, these interactions that we've introduced render the neutrino medium opaque. So they have an opacity. And this opacity will be proportional to this dimension full coupling constant, G effective squared, which is directly proportional to this G nu I had on the previous slide, which characterizes the strength of the interaction. And this opacity, its main role is just to delay the onset of neutrino free streaming until later times than in the standard model. So this is illustrated here. So this plot shows the neutrino visibility function, which characterizes essentially the redshift the neutrino last scattered from these new interactions. So and as you make this interaction strength G effective larger and larger, what happens is that you delay on the onset of neutrino free streaming until lower and lower redshift, which is shown here on the z-axis. So the point of these interactions is really to delay neutrino free streaming until later in the universe. Now, because you delay this free streaming, and neutrinos essentially now behaving like a tightly coupled fluid, you don't have this behavior that neutrinos can get ahead of the photon baryon plasma sound wave anymore. So there's no longer this kind of gravitational tug that neutrinos can exert on the photon baryon. And that means that this phase shift and amplitude shift that was there before in the standard model is no longer there. So you've undone, if you want, this amplitude and phase shift. So that, you know, if in the standard model, the photon would have a sound wave like in the green line, but now they're gonna be have a sound wave much like this blue, this red blue line here. And so there'll be a net phase shift to slightly smaller scales, where as a slight amplitude increase compared to the standard model. Now, if you actually just translate these effects on the CMB power spectra themselves, we can see how that works over here. So here I'm illustrating the fractional change to the temperature cosmic microwave background spectrum as normalized to lambda, the standard lambda CDM, as a function of L mode here, or angular scales, with, you know, large L being small scale, smaller L being large scales. And I just want to draw your attention here to a couple of these lines, of these curves that I'm showing here. First, I just want to draw your attention to this dotted black line here. This line is just lambda CDM standard cosmology, but I've just boosted the energy density in neutrinos by essentially like one extra species, if you want. And because this essentially increased the Hubble rate at early time, this leads to a net suppression of the spectrum compared to lambda CDM. So you see this is suppressed, you know, at a 10% level at large L here. And I also want to draw your attention to the red line here, where here I've left the energy density of neutrinos unchanged, but I've delayed the onset of neutrino free streaming until quite a bit later than the standard model. And because now you do not say have this kind of damping effect and phase shift effect from neutrino free streaming, you see you get a net increase in temperature power compared to lambda CDM. So this red line is above zero now, again at the 10% level or so at large L. And now if you combine these two effects in the dashed or dotted red line here, you see that which is, you know, kind of more following the data points here, you kind of cancel the two effects. So you can, you know, adjust the spectrum by both increasing the energy density of neutrinos and making them non-free streaming, and these two effects tend to be opposite in sign, and so you get, you know, something that's somewhere in the middle and provides a better fit to the data. Now, of course, here this is not a fit. This is me just changing two parameters at a time, but you can see in principle that, you know, having non-free streaming neutrinos could be compatible with having more neutrinos as far as the CMB is concerned. Now, if you do ask the question from the CMB data, you know, what does the CMB data say about neutrino free streaming at early times? Phrase here in terms of this G effective, this new interaction that I've introduced in this model. And the answer you get is kind of interesting because you get basically two statistical modes. It's a bimodal answers where kind of focusing on this panel down here where you have a mode that corresponds to a fairly large value of this coupling constant, which of course corresponds to a quite a bit delayed onset of neutrino free streaming. And then you get the second mode here, which is much more consistent, if you want, with lower value of this coupling constant or an earlier onset of neutrino free streaming. And you can see from this plot that this bimodality is made possible because of a multi-parameter degeneracy between this coupling constant G effective and things like the amplitude, the scalar amplitude of structure in the universe, as well as the spectral index, NS, which tell you about the tilt of the primordial power spectrum coming from inflation or what have you in the early universe. Now, just from the nomenclature perspective, so this big mode here, a very large G effective value, we can call this the SI-nu, the strongly attracting mode. And this mode here that kind of smoothly connect, maybe more lambda CDM universe, we're going to call this the moderately attracting mode, or the MI-nu. It is interesting to kind of separate these two modes to see their impact on important parameters like, say, the Hubble constant for instance. So if you just look at this middle panel here, you see that, if you do have a delayed onset of neutrino free streaming, you can actually have a large value of the Hubble constant being compatible with potentially with CMB data. And we're gonna just come back to this in a second. So that was kind of interesting. I just want also to draw your attention to this this other panel here, which actually is the phase. This data star is essentially the phase of the CMB spectrum, and it's pretty clear here that you see the phase shift that I've been telling you that is caused by having neutrino free streaming versus not having neutrino free streaming. By comparing, say, the gray line here, which is lambda CDM, to this kind of solid red line, you do see the two spectra are shifted by a fairly large amount. And this is really the impact of having a delayed onset of neutrino free streaming. This phase shift is really there in the data. All right, so how does it work? How do we get a larger value of the Hubble constant from introducing neutrino self-interaction? So it's kind of a two-step process. And to really understand this, I'll have to describe a little bit how we infer a value of the Hubble constant from CMB observation. Now, CMB observation, just make a map of the sky. It's a two-dimensional map over the celestial sphere. And we can, of course, decompose this map into Fourier modes and so on. But apparently, our data is really a 2D map of the sky. And this map has cold spot and hot spot, as I mentioned, cold spot and hot spot, I mentioned earlier. And we can, we're very good at measuring the typical size of a typical hot spot or typical cold spot. And so essentially what we're measuring are angles on the sky. And there's one key angle which is related to this phase I just mentioned in the previous slide that we're measuring very well. And this is the angular size of the sound horizon. And the sound horizon I'm talking about is essentially, how far this baryon photon sound wave traveled in the early universe prior to the epoch of recombination. Now, so we measure the size in the sky, the angular size of the sky. Of course, you all know that an angle is always a ratio of distance. And the distances that enters this angle here are the ratio of the sound horizon, so the physical distance that the photon baryon sound wave traveled at early times, divided by the distance between us and the last scattering surface of the CMB, where the CMB was emitted. And it turns out that these two distances, are sensitive to different things. The sound horizon is really sensitive to what's going on in the early universe, while the distance between us and the CMB is really sensitive to the Hubble constant. It's much more of a local kind of thing. So what is the story with neutrino self-interaction here? So one thing that happened is that if you do have neutrino self-interaction, you can actually increase the energy density at early time independently. So you increase the energy density, and that via the Freeman equation, it increases the Hubble rate at early time. And because the sound horizon RS depends as 1 over the Hubble, you essentially can suppress the size of the sound horizon by increasing Hubble. Now, usually when you do that without neutrino interaction, it's horrible because there's a bunch of other changes that happen to the cosmic microwave background spectra that leads to a terrible fit into the data. And so these kind of solution, if you want, are not very favored. However, if you do have neutrino self-interaction, you essentially undoing some of that damage because you're not overdamping or overshifting the CMB spectra once you add energy density within the neutrinos. And that's really the key here, the fact that you can undo some of that damage because you're not overdamping, overshifting the CMB. And because of that, so you shrunk RS, And in order to get the angle here to be the same, you also need to shrink the A. And the way you can shrink the A, because this is sensitive to 1 over h again, this Hubble rate, this leads to a higher value of the Hubble constant just to keep the angle in the sky fixed. So you add energy at early time, and you get a larger Hubble constant inferred from CMB maps. So this is kind of how it works. So the neutrino self interaction really plays the role of trying to correct from the damage that having extra energy density in neutrinos actually impact on the CMB. And any kind of residual change that you have to your CMB spectra can be absorbed by changing the primordial spectrum of fluctuation, which is characterized by an amplitude, AS, which I mentioned earlier, as well as the scalar spectral index, NS. And this was part of this multi-parameter degeneracy that I mentioned earlier. Now, the key question is, does this really work? And it's actually, the answer is no. It appears extremely unlikely that neutrino interactions alone can really address the Hubble tension. And you can really see this in this panel. And the cause of that is because we've measured the CMB so well, and including we've measured the CMB polarization very well by now. And the CMB polarization is very sensitive to the phase of the CMB sound wave, if you want, going on in early times. And the fact that we measure this phase so well really constrain the amount of energy density you can add to the neutrino sectors, as well as the the amount of self-scattering you can add to the neutrino sector. And you can see here, in this kind of green contour in this plot, which is, the data set here that includes Planck polarization, that the value of the Hubble constant you get is quite a bit lower than, say, the green contour here, which does not has polarization. So, so polarization is really constraining, and it tells us that it's really difficult for just neutrino self-interaction to really address the Hubble tension. Now, even without just kind of forgetting the fact that we have this Hubble tension within our cosmological data right now, there's still funny things happening within the realm of neutrino interactions and cosmology. So depending which kind of data, CMB data you ask the question to, you can get very interesting or slightly disturbing answers. So here's an analysis that was carried out actually by other folks, asking the same question we've been asking, what does the CMB data tell us about neutrino interaction in the early universe? And you get these kind of posterior here, again, phrased in terms of this G effective here, and you get this fairly strong preference from a delay for delayed onset of neutrino free streaming. Again, in these units, the standard model would be at about -11. So this is a very strong preference for much stronger interaction than electroweak. It's just very puzzling what this means. And on the right panel here, you add Planck data. In general, Planck data with all the polarization power that it has slightly disfavor this, but and kind of restore at least some statistical weight at smaller G effective value. But still, there's still this hint for something strange going on in the neutrino sector, even outside the realm of cosmological tension. Now summarizing this part of the talk, which was concerned with CMB and neutrino interaction and the Hubble tension. So CMB data can be made compatible with the presence of a neutrino self-interaction because of this multi-parameter degeneracy that I mentioned between interaction and effective, as well as a primordial spectrum of fluctuation. However, once you include Planck polarization or other polarization data, really, that and because of that, you're measuring the phase shift very well, you tend to disfavor the presence of these interaction, at least as a solution to the Hubble tension. But nevertheless, even without the presence of tension, there's still some kind of strange hint that CMB data at least is compatible with some level of neutrino self-interaction at early times. Now, if you'd like to understand a little bit better what's going on, we're going to need to kind of put the CMB aside for a little bit here and try to find an independent probe for this neutrino interaction. And this probe is going to be the large-scale distribution of galaxies, which is a completely independent probe of the growth of structure and the cosmological evolution, which will, with Rubin and Desi, and is an exploding industry right now. And so we want to use this large scale distribution of galaxy, and of course, just like the CMB, the way we capture Statistically, what's going on here is through their power spectra. So here, the kind of full shape galaxy power spectra that we're going to use in our analysis to try to learn something about neutrino self-interaction in the early universe. Now, of course, galaxies are bias tracers of the matter. So whenever we do these analysis, we need to do the kind of the full analysis, including galaxy bias and nonlinear correction and all this. And of course, in everything I'm going to be presenting today will include these effects. Now, neutrinos and everything else in cosmology, they all couple to each other via gravity. So if I change the properties of neutrinos, whether they're streaming or not streaming, the dark matter, which otherwise doesn't talk to neutrinos, will know about it purely gravitationally. And it turns out that this is a very important fact, because neutrino fluctuation, the way neutrino fluctuation grows or not, is really sensitive to what neutrinos are doing. Because neutrino, again, are like 41% of the energy density at the early times and the only free-streaming species in the Sedent model. So they play a very important role. And to understand that, of course, you're going to have to solve some Boltzmann equation for the dark matter fluctuation, which is this equation in the presence of gravitational potential, which are sourced in part by neutrinos. Now, here's a plot trying to illustrate the impact that neutrinos, the new physics in the neutrino sector can have on dark matter fluctuations. So I'm going to focus your attention here to this lower right panel here, which illustrate the ratio of some gauge invariant dark matter density fluctuation as normalized to their lambda CDM counterparts. And the different color lines illustrate the three different wave numbers, a fairly large wave number in purple, a kind of intermediate one in red, and a small k or very large scale one in blue. And so let's look at the evolution of these three wave numbers as they become causal, enter the horizon, and start evolving, which happen when this thing kind of goes away from one here in this plot. So first on the purple line, so this is actually a Fourier mode that in this cosmology here will enter the horizon, become causal, and start evolving before neutrinos start the free stream. And when this happened, because the gravitational potential behaved differently, whether neutrinos are free streaming or not free streaming, the dark matter density fluctuation will be suppressed in this case. So there'll be this evolution. It looks like there's a little bit of an enhancement at first, and then there's a net suppression at the at the 5-ish% level, because neutrinos were not free streaming when this density mode, and became causal at early times. Moving on to the red wave number here, this is a very, very special wave number, because this is a wave number or density fluctuation that becomes causal exactly when the neutrinos are starting to free stream. So you have the peak of the neutrino visibility function, and because of that, neutrinos, the dark matter density fluctuation gets a net enhancement compared to lambda CDM, which is what this red line shows. Not as about like 5%-ish enhancement, because this mode enters the horizon exactly when the neutrino starts free stream. And then moving on to the blue, which become causal very late when the neutrinos have been streaming for a while, and then there's essentially no change with respect to lambda CDM, and this blue line is just 1 because it's just lambda CDM essentially for this mode. So kind of putting all of this together, what you get in terms of the matter power spectrum describing these dark matter density fluctuation on different scales, you get this behavior that on large scale is basically lambda CDM. So this plot illustrates the ratio of an interacting neutrino cosmology respect to a lambda CDM matter power spectrum. There's a function of wave number here. So on the very large scales, there's low k, there's no change. Everything is just exactly lambda CDM. But then as you get close to the epoch at which neutrinos start to free stream, you get this enhancement that I was talking about, because gravitational potentials just behave differently as neutrinos start to free stream. And then, at very small scales, which are mode that enters the horizon when neutrinos are not free streaming, you get a suppression. So this is the kind of typical shape you get for these models, where there's like a scale that gets enhanced, and then you get a suppression. And some of these other lines on this plot shows different G effective, so different strength. So if G effective is smaller, this bump occurs on smaller scales because things happen earlier. And also show different neutrino masses, because of course neutrino mass has an impact on the matter power spectrum, but the impact of neutrino mass is essentially additive, if you want, to the impact of the interaction here, as you can see from this plot. So now we can ask the question, what does the data from the galaxy, the large-scale galaxy distribution, tell us about neutrino self-scattering? So here's an illustration of that. So here I'm illustrating both the monopole on the left and the quadrupole power spectra on the right. And these are both data point in gray. And I just want here to draw your attention to this lower left panel here, which is essentially a ratio again of interacting neutrino cosmology to the lambda CDM counterpart. And I'm just going to focus on the solid blue line here, which is an interacting neutrino model with a very strong interaction that is a very late onset of neutrino free streaming. And you get this kind of enhancement here because you're kind of riding this kind of big bump, right? Because of these are the mode enter the horizon at the onset of streaming. And it looks like it's a terrible fit to the data. But again, just like the case of the cosmic microwave background, you can adjust the pyramidal spectrum of fluctuation, NS and AS, to transform this solid blue line into the solid dashed line here. And then, get a much, much better fit to the data. So it's a very similar story where, you have some impact from neutrino free streaming or not, and then you can compensate some of that by changing your pyramidal spectrum of fluctuation. Now we add the question. So we asked the question, we took these data, so we add the question, what does the data say about a delayed onset of neutrino free streaming? And here, so we did a profile likelihood analysis where we tried to essentially find the best fit cosmologies as a function of G effective, as a function of essentially the onset of neutrino free streaming. And again, we find this minimum in this chi-square surface at this strongly interacting neutrino cosmology, or G effective around minus 1.5 or so. And that indicates that somehow the large scale structure data seems to favor, again, a slight delayed in the onset of neutrino free streaming as compared to lambda CDM. So this is interesting because if you look at the model that corresponds to this best fit, which is going to be here, this purple curve here, this purple curve. And again, this is a ratio of the matter power spectrum for this interacting neutrino cosmology with respect to lambda CDM. And we see that in this model, you get a net suppression of the matter power spectrum at small scales. And this is interesting in the context of cosmological tension, because of course we have this SA tension, which seems to indicate that the amount of structure in the universe, or the matter amplitude, is slightly smaller than we expect. And then here's a model that actually predict a smaller amplitude of matter fluctuation. So here, this is one potential way that interacting neutrinos could be addressing the cosmological SA tension. Now, I just show you a likelihood profile analysis. I can also show you a kind of standard full-blown Bayesian analysis, but the answer is essentially the same. We see a preference in the data of the full-shape galaxy power spectrum for a delayed onset of neutrino free streaming. And again, in this panel here, we see this lower value of sigma 8 or S8 that comes out because we have these neutrino interaction. You have this kind of tail that extends to lower value because of this interaction. And what's interesting here is that this model, with the G effective around minus 1.5 is very similar to what we got when we asked the question from cosmic microwave background data. So now we got, interestingly, two different independent data set, large scale structure and CMB, telling us that each have some compatibility with a delayed onset of neutrino free streaming. So this is kind of interesting. And I want you to keep this in mind. Now, kind of summarizing the impact of the neutrino interaction on SA tension, because you get the suppression of matter fluctuation at early times, neutrino self-interaction can address the SA tension on their own. But the question is whether you can do this while maintaining consistency with the precise measurement we have from CMB data. And that's really what I'm going to talk about next, because we have a preference from CMB for some delayed onset of neutrino free streaming. We also have this preference, but are they compatible with each other? And this is actually a little tricky to do. And it turns out that if you ask the question, if you do a joint analysis of CMB and full shape of the galaxy power spectrum, you get results like this. And it turns out it's actually very difficult to address both the S8 and the H0 tension with just CMB neutrino self interaction. So if you look at some of these panels, right here, S8, And we have, the strongly interacting neutrino mode here in green, as well as some much more lambda CDM in purple here. And we see the value of SH are fairly large, they're very compatible with what we have in standard lambda CDM. So you don't really address the SA tension. And then in this panel, we illustrate H naught, and you see that, in all these analyses, H naught is pretty low compared to distance ladder-based measurement. And as you combine these two data sets, the large scale structure and the CMB, the preference for a delayed onset neutrino is very marginal. And the reason for that is that the two kind of data set, while they kind of each favor separately somewhat some delayed offset of neutrino free streaming, they actually prefer different values for the other cosmological parameters. So if you try to combine them together, there's a tension. It's kind of incompatible in some ways. And I do want to mention that somehow the jury, despite that, the jury is still somewhat out there about this old picture, because if you consider, say, other probe of large scale structure, or maybe small scale structure in this case, like the Lyman alpha observation, which probe K of 1 or so, and you ask the question again, what this data thinks about self-interacting neutrinos, there tends to be a very strong preference for delayed onset neutral free streaming, as shown in this kind of red line here, which has Lyman alpha data included. And again, what's happening here is that Lyman alpha data, it's well known, tend to favor quite a bit of a suppression on small scale for the amplitude of matter fluctuation. And here is a model that naturally has a suppression. So if you ask the question, you're going to get a strong preference for these neutrino self-interaction. It does not mean that the suppression is caused by neutrino self-interaction. It could be caused by other physics, but it's nonetheless interesting that the jury is still out there about what's going on here. Of course, this is really difficult to interpret. It's the Lyman alpha data. It's in contradiction with other large-scale structure data, so the jury is still out there about what's going on here. Now, kind of summarizing the current situation about cosmological tension and neutrino interaction. I think it's pretty clear that both the CMB and the full shape of the galaxy power spectrum could be made compatible with non-vanishing neutrino interactions. But however, separately, they kind of prefer slightly different cosmologies, and that makes them in tension with each other, large scale structure and the CMB. And which means that we don't really have a concordant picture with just simple neutrino self-interaction. And here I said it, what we've done so far is very, very simple. It's a very simplified model. We don't have any flavor structure. It's the simplest interaction I could imagine writing down that I've done here. And the fact that the two kind of data sets prefer different cosmology might be an indication that whatever model we're using is not accurate enough, that we really need to have something more realistic to compare with data if you want to have a concordant picture. And it's pretty clear that overall, in this very simplified picture presented to you so far, we cannot address the H naught and SA tension uniquely with self-interacting neutrinos. Now, the future prospect, it's really about trying to find better models that are actually realistic. We have a lot of laboratory constraints on neutrino physics, and we need to take these into account. And it's pretty clear that it's kind of universal interaction when every neutrino couples to everything else. It's not very realistic, and we're going to need to do better to actually make consistent analysis. And it's pretty clear from some analyses that people have done that having a flavor structure in your interaction, that is, not every flavors or mass angular state interact the same way. It's probably pretty important in terms of fitting the CMB, including the polarization data. Here's a work from Dash and Ghosh showing that depending, how many flavors or species are interacting versus not interacting, you get different kind of fit to the CMB data and different kind of preference for this delayed onset of neutrino free streaming. And even beside trying to build these interactions, there might be completely different ideas. Like if you have an extended dark sector that somehow talks to neutrinos, can also result essentially suppressing the neutrino free streaming without having to, a very, very strong interaction that are, 10 orders of magnitude above electroweak. So this is a very interesting model by Aloni et al. That essentially has this complex dark sector that mixes with the neutrinos. And as far as cosmology is concerned, what it really does is that suppress neutrino free streaming, which is a very similar kind of theoretical model to what we have considered without all the baggage about having this very, very strong interaction kind of floating around. So there's interesting ideas that could be more explored more and might provide a better fit to the data. Now it's time to wrap up here. I'm running out of time. So hope I'd convince you that neutrinos are a very important portal to probe new physics in cosmology. And cosmology in turn, because neutrinos are so important at early times, is a good testing ground to see whether we have new physics in the neutrino sector. So here in this talk, I've focused on very simple model, just two parameters, N effective and G effective, and see what these models could do for cosmological attention, but also more generally in terms of constraints that we get from CMB and large scale structured data. Now it's pretty clear from everything we've done so far that just self-interacting neutrinos alone are not going to address, the S8 or the H0 tension. I think that should be pretty clear. So you're probably going to need other things, at least in addition of that. But nonetheless, from all the analyses that we've done and other groups have done, that CMB and large-scale structure have interesting hints for a delayed onset of neutrino pre-streaming, and these hints should be thoroughly investigated in the context of more realistic model to really determine what's going on there and see whether we have hints of new physics in the neutrino sector. So let me stop here. I'd be happy to answer any question in the live session later, and I hope you enjoy this talk. Thank you very much.